Here is Nicholas Miller. He's an assistant professor in the Electrical and Computer Engineering Department at the Michigan State University, and he was formerly an electronics engineer at the Air Force Research Laboratory for 6 years. Professor Miller is currently a young professional member of the IEEE TC3 committee. His current research interests include linear and nonlinear millimeter wave characterization of on-wafer transistor and integrated circuit, physics-based compact modeling of compound semiconductor transistor, and technology computer-aided design modeling of wide and ultra-wide bandgap semiconductor transistors. Dr. Miller was a recipient of many awards. I will mention the Best Paper Award at the WAMICON conference in 2021. The FRL Early Career Award in 2023, and also the Best Presentation Award at the virtual workshop that we yearly have dedicated to young professionals. So that's an event that is virtual, just as this one, and typically takes place in the fall. So stay tuned for the next event. Now, Nicholas, please, the floor is yours.
Okay, can you hear me okay?
Yes.
All right, great.
Thank you.
Thanks, Gianpiero. Hello, everyone. Thank you for staying tuned here. Saw a few people leave. I'm used to that when being the last talk. But thanks for everyone for joining. And again, thanks, Gianpiero, for the kind invitation to talk here. So I will present today on maybe a little bit more higher frequency applications. So I kind of titled my talk W-band GaN HEMTs, and then dramatic, a perspective on characterization and modeling. Okay. So I'll try to keep an eye on time here, just so I don't go too long. So I'll start with kind of a quick overview of applications and specific transistor technologies for W-band. And then I'll show some, give some references for state-of-the-art GaN HEMTs and MMICs that are published today. Talk a little bit, or maybe a decent amount, on a few important things for W-band circuit design, and that would be on-wafer W-band load pull measurements and modeling. And we'll finish up the talk on wafer W-band noise parameter measurements. And we'll have a quick summary here. Take a sip of water. So applications for W-band frequency. A lot of really great examples out there. Just pulled a couple more, a little bit older papers, but I think are still relevant today. For W-band, as we get higher in frequency, some interesting applications include, it's my third bullet, but the first one I'll talk about, some directed energy applications. So have a very interesting paper from back in IMS 2016 on a 7 kilowatt GaN W-band transmitter. Also for W-band frequencies, some interesting applications include radar, high resolution imaging. So I have another example of some W-band applications here. What I really want to start the talk off is a lot of these applications, as you can see, 7 kilowatts, crazy high power. A lot of these require high power density transistors at W-band in order to either get the power that you need, radar range that you need, image quality. So high power density transistors. So let's maybe look at the landscape of available transistor technologies that will work at W-band frequencies. So of course, whenever you start a talk like this, you'll reference now the ETH power amplifier survey. So I've done that here. But first, I kind of want to start with this nice paper that shows kind of the landscape of available, what we'll maybe say millimeter wave transistor technologies. And your usual suspects are here, including silicon, SiGe, and indium phosphide, gallium arsenide, and have kind of a plot here that I stole, but referenced, of plotting FT versus Fmax. And so again, we see silicon, indium phosphide, gallium arsenide, but sitting right in the middle is gallium nitride. So it's not quite the best, it's not quite the worst in terms of high frequency. But again, when we look at the power amplifier survey, I've got the gallium nitride power amplifier examples. When we start to look at for maybe like radar range or directed energy applications, what you really need is power and being able to deliver power efficiently. Now you start to see gallium nitride is very interesting above 50 gigahertz. And it kind of has a sweet spot at W-band frequencies where it's high enough frequency-ish, it has a decently high FTF max, but it can deliver the power and has high power density. So gallium nitride HEMTs are very excellent transistor technology for W-band applications. But of course, as we know, as we've seen through the talks today, challenging to characterize and model properly. And no small feat to do so at W-band. So I'll show a few examples here of state-of-the-art W-band gallium nitride HEMTs. First slide here, a couple examples from HRL laboratories in the US. The first one is what they kind of call T3L. It's the graded channel GaN hemp, kind of pioneered and championed by Jung Moon at HRL, and has seen some really nice W-band power results and some very nice linearity results from this T3L process, and have a really nice, cross-section image here, some beautiful imaging and some very interesting technology out of HRL, this graded channel. In addition, there is this T3.5, kind of Dan Denninghoff is leading that effort there at HRL, and demonstrated some very high FTF max for gallium nitride and some really nice power density and efficiency. So here's a couple examples with a couple papers here for state-of-the-art W-band GaN HEMTs at HRL. And then this is certainly not a complete list here, but trying to just survey a few papers out in the literature. Some nice new 90 nanometer GaN technology developments out of BAE Systems. So here's a paper that I'm happy to share and you can find online. Also Fraunhofer IAF, has for many years had very, very nice millimeter wave GaN technology and performances and mimic demonstrations. This one here is a low noise amplifier example from Fabian Thum, and there's some really nice other really interesting results there. And then third, again, this isn't complete, but this is a third example to just kind of bring up as we're talking about W-band state-of-the-art GaN HEMTs. Some really nice results coming out of Teledyne Scientific in the USA by Keisuke Shinohara. So there's this multi-channel Schottky barrier height, this bridge HEMT technology, also very interesting. So a few examples of state-of-the-art W-band GaN HEMTs that could be interesting to look at. And then of course, it's interesting to have a very brief and definitely not thorough analysis of state-of-the-art W-band mimics, GaN-based mimics. So again, one example is, this might be the exact same paper here, but here's now an actual mimic demonstration out of Fraunhofer. Here's where HRL, their graded channel, they made some nice high power density W-band power amplifiers. A really cool example, in my opinion, is a 100 watt W-band GaN SSPA from this paper, this group, Raytheon. And then I definitely encourage the crowd, if you're interested, and if you haven't seen it already, Tim Sonnenberg and Zoya's group have a really nice paper in IEEE Journal of Microwaves, where they kind of summarize and show some of their work in terms of V and W band GaN mimics. So this is just kind of a quick survey of the technology mimic demonstrations. Sorry, I'm going to take a drink of water. So now if we start to look at what is needed for this W-band GaN design cycle, really we need precise, I really want to foot stomp and highlight precision on wafer load pull and noise parameter measurements, and maybe I'll show some examples in a few slides, maybe some thoughts on precision measurements. And also, once we have confidence in precise measurements, we need to be able to extract accurate linear and nonlinear circuit models to do circuit design. So obviously seems straightforward, but it's useful again to think about what's really in the requirements on the transistor characterization and modeling side: precision measurements, accurate models. So let's talk a bit about on-wafer W-band load pull. I'm going to keep an eye on time because I could talk about this for a while. as a lot of presenters could. W-bands on wafer load pull, systems have been around for quite a while. I've got one example here that's at the Air Force Research Laboratory, an on wafer scalar load pull system. There's also commercial solutions here, and I think you'll see a little bit about this in a following session today from Mori Microwave, and then also commercial solutions from Focus Microwaves. In my opinion, requirements for on-wafer W-band load pull systems, we really need to have high power and high dynamic range in the system. High power so that we can, if we're characterizing GaN, be able to push it to compression. If we're talking about active load pull, we certainly need high power to achieve high gamma at the load, but we really need high dynamic range as well, being able to measure from low input power to high input power and having a quality calibration across that range as well. I think I want to show some examples here that will provide some quantitative evidence for the following statement, but I think for W-band frequencies and up, we really need to start thinking about making it a requirement to do on-wafer multi-line TRL calibration in order to properly characterize. So this is now getting into the precision measurement aspect. So let's dive into this a little bit more. So recently published, I guess recently, more than a year ago now, but time's flying these days. Recently published, though, an on-wafer W-band load pull calibration study in Journal of Microwaves. So happy to share this paper. And I want to discuss some of the results and talk about the repercussions in terms of on-wafer W-band load pull characterization. So essentially what we did was, this is a calibration study. We were lucky enough to get a single GaN die that had the same nominal chip in both compacted CPW form. And I've got a picture on the next slide to clarify this, but I wanted to start with, here's what we did. We had one die and we had the same intrinsic transistor put into a compacted CPW form where we had to use off-wafer probe tip LRM calibration. And we had the exact same nominal intrinsic device in what we call an extended reference plane device, which had the proper on-wafer, a very well-designed on-wafer multi-line TRL cal kit structure. So we had the same nominal device measured in two different configurations, most importantly measured with two different calibration approaches, off-wafer LRM calibration and on-wafer multi-line TRL. And the bottom line up front was we observed pretty inconsistent results with the off-wafer LRM calibration, but very consistent results with the well-designed on-wafer multi-line TRL. So to kind of, pictures are worth 1,000 words, and I'm a very visual person. So again, we had the same nominal GaN HEMT, millimeter wave GaN HEMT. So we'll say inside the box was exactly the same, but we had two copies of that intrinsic device, one in a compact CPW configuration that had no on-wafer calibration structures associated with it. So we had to do off-wafer calibration, LRM calibration. And then we had the exact same intrinsic device in an extended reference plane, so with additional transmission line. And these transmission lines, in addition to this structure, we had the multi-line TRL calibration structures. So we were able to measure nominally the same device, and we measured them in the exact same way, but with different probes and different calibrations. So again, with the LRM calibration, maybe this is getting into the weeds, or maybe the audience is familiar with this. With off-wafer calibration, our reference planes are really established at the probe tips. With on-wafer multi-line TRL, it's just the reference planes are established at the ends of the half of the through, or the launcher, as we call it. So this is really important because the on-wafer multi-line TRL includes the probe transition to the GSG pads with the same substrate from the calibration, whereas the off-wafer calibration, it's very important that it's a different substrate, specifically different dielectric. So dielectric constant of the substrate. So this is really important. And now let's look at the repercussions. So what we did is first we did S parameter measurements with these two devices with 3 different types of probes. And we compared just the 3 measurements with the off-wafer calibration with 3 different probes at the exact same quiescent, exact same operating condition. And then we compared the exact same 3 sets of probes, but with the on-wafer multi-line TRL calibration. This is where I said I didn't lie. I could talk about this for a while, so I'll try to speed up. But getting into the results here, now I'll have them binned as what we'll call LRM. That's the probe tip calibration off wafer cal. This is the same nominal device, same bias, just measured with 3 different sets of probes. And to try to be a little bit succinct versus frequency, this is a a relatively broadband S parameter measurement system. We just reported here G max and dB, and you can see I've highlighted here at 94 gigahertz. You can see a very big difference between measurements of the exact same transistor, just with different probes. So this is a very inconsistent result that we saw with LRM, but when you do the exact same 3 sets of probes, but now calibrated with the on-wafer multi-line TRL structures, and you measure that extended reference plane device 3 times, very, very consistent results. And so this is what I want to try to convey, this message that on-wafer multi-line TRL, I think is critical, even at what you would think maybe lower frequency. Maybe it's high frequency for you, but for the terahertz people, W-band is kind of low frequency. Even at these frequencies though, sub 100 gigahertz, the on-wafer multi-line TRL calibration is really starting to have an impact. And so I think we really need to start pushing on using this type of calibration for transistor, on-wafer transistor characterization. Now, if we repeat the same study with the load pull system, we only had 2 sets of probes. I have them labeled here, but 2 different sets of WR10 probes. We recalibrated the system 2 times with the off-wafer calibration, and we measured the CPW device. And we can see we saw very, very inconsistent results, up to more than 24 points, not percent difference, but total points difference between measured power added efficiency of the exact same device, exact same bias, exact same operating conditions, but just with 2 different sets of probes, both calibrated off wafer. This is very inconsistent results in my opinion. And then if we did the exact same 2 sets of probes, but we calibrated the load pull systems with on-wafer multi-line TRL and then measured the extended reference plane device, very consistent results with 2 different sets of probes. So clearly you could get a pretty big discrepancy measuring the same transistor with different sets of probes. I think we need to, again, this really is quantitative evidence in my opinion that we need to start pushing towards on-wafer multi-line TRL for precision characterization of GaN HEMTs. And I see some chat and Q&A. I'll try to catch that at the end. So I think that the other than trying to ensure first pass design success, which foundries are very interested in, I think it's also really important to highlight this when we start to show W-band load pull benchmarking plots, because we're getting kind of muddied waters of comparing some results that are off wafer calibrated with some results that are on wafer multi-line TRL calibrated. And as I just showed, if someone measured their transistor with 2 different sets of probes, maybe that drastically changes the performance. So I think we really need to start highlighting this and say, like I have here. So I pulled a couple from a couple papers here, recent papers, some of the benchmarking plots that you've seen specifically for GaN. I've tried to highlight which ones were the multi-line TRL calibrated and which ones were the LRM calibrated. I think we should start to highlight this. And I think that it gets a little bit muddy, but it's difficult to compare those 2 sets of data sets. And so in my opinion, I think we should separate them. We should compare just the LRM calibrated measurements with LRM, and we should compare MTRL. And I think the proper way to do this is with multi-line TRL calibration. So if this was interesting, this is a good chance to highlight an IMS workshop that I'm organizing and hosting this year in, I think, Washington, D.C. So it's on Monday. It's an all-day workshop, and the title is On Wafer Millimeter Wave Load Pull for Beyond 5G Microelectronics Characterization. We have a really nice set of international speakers. So if you really liked the discussion on wafer W-band load pull, happy to invite those that are attending IMS to think about this Monday workshop here. It's a little bit of shameless plug there. So let's get back into, I think I'm maybe running a little bit long. Let's get back into talking about a bit more of W-band load pull assessment of transistors. If we look at kind of a typical Smith chart coverage that you'd get with a passive tuner system, you can see it's considerably less than the entire Smith chart. And it always works that it's always shifted in frequency. And of course, whenever you try to characterize the device, its optimal impedance is always at where you have the lowest gamma. Of course, it always works like that. It's like the system knows. But you can have anywhere from 0.5, 0.6 to 0.7 gamma, depending on phase. But this is a difficulty of measuring on-wafer W-band GaN HEMTs, is that since most of them are unmatched, you aren't able to get to the optimal tuning conditions. So how do we mitigate this? Active load pull is one approach to this, but I would say active load pull is not a silver bullet. It definitely has high power requirements. So I think modeling is an interesting approach to try to surmount some of these passive tuner systems, or maybe approach a combination of both active load pull and modeling. What I'll just talk about today, and maybe I'll go a little bit more quickly because I think I'm going really long here. I'll show a little bit of examples for GaN HEMT physics-based modeling here. So here's just kind of a quick example with a paper if you're interested to look at it. These are some older results here, but just showing some accurate GaN HEMT nonlinear modeling from X to Ka band, just to kind of prove that we can do an okay job compact modeling here. But here's maybe one of the more recent examples of W-band GaN HEMT nonlinear modeling built upon on-wafer W-band load pull. I want to highlight that, like I'm true to what I said before. This was probe tip LRM calibrated data here. So here's a few examples of the measured versus model. It's okay, and then a few load pull contours compared measured versus model looks pretty decent, and then a pretty okay looking power sweep comparison measured versus model. So now that we have a nice model here, we can consider going beyond the passive tuner characterization range to be able to fully quantify the optimal impedances for this transistor. So this was kind of the concept here, this kind of older RF tag paper, where we just used the model to simulate beyond the dashed lines here that are the passive tuner range. So maybe this is one example of how to use W-band GaN models to do both characterization and modeling. And then this is kind of the final result here of showing a comparison of the measured efficiency compared with the optimal efficiency given by this ASM model at 94 gigahertz. Okay, actually, I think I'm in good shape. So talked a little bit about, maybe more power amplifier relevant characterization and modeling. So I'll show a little bit about on-wafer millimeter wave noise measurements. Obviously, this is critical for LNA design, for low noise transistor modeling. I do want to highlight, the talk today is on W-band GaN. It's certainly not the superior technology for noise, but performance is getting better as gain is increasing. And again, W-band is kind of, in my opinion, a bit of a sweet spot for GaN, in terms of trying to compete with the really high frequency processes. So performance is getting better, and it's interesting to think about characterizing GaN at W-band noise parameters of GaN, and using that to maybe think about doing some, transceiver design on the same IC. So again, another shameless plug for papers, but I really liked this paper. Happy to put this up and share if you want to go download it, but this was a cool example where we were able to collect, from 4 different foundries in the U.S., 6 different millimeter wave GaN HEMTs processes, 6 different types. We were able to measure all of this. So I call it a survey, but it was all fresh data that we measured in our lab. And this was really a fun example to try to put forth this first example of, a benchmark plot or benchmark data set for noise parameter performance of GaN. So we were able to work with, we're very happy that these foundries worked with us, BAE, HRL, Northrop, and Teledyne, and able to measure these. And we were really trying to compete for the award for most authors in IEEE Journal of Microwaves. I'm not sure if we won that award, but so here's just a quick example of some millimeter wave GaN noise measurements. We were able to measure what I'd called ultra broadband noise parameter measurements. It was with 2 different systems, an 8 to 50 gigahertz noise parameter system from Mori Microwave, and then a W-band noise parameter measurement system. And we came up with an idea to stitch the data sets together to get 8 to 110 gigahertz noise parameter measurements. And so this was a fun example here, and showing a few of the benchmark results from the foundries here. So, a good first example of on-wafer noise parameter measurements of GaN at W-band. And one thing I do want to highlight is, maybe now it's becoming clear, if you've seen this paper, I binned the measurement data sets into both LRM calibrated and MTRL calibrated. And it's for the exact reason that I had just discussed, that I don't think it's proper to compare directly the two different calibrations. So that's why we put those. So the paper's a little bit lengthy because I binned data sets into probe tip calibrated and MTRL calibrated. And maybe now it's starting to become clear why I did that. So here's an example of W-band GaN noise parameter characterization. So actually, I think I'm pretty decent on time, maybe a little bit long, but in summary, W-band GaN, I think GaN's very interesting for W-band applications. In order to try to approach first pass design success, we really need to have precision measurements and accurate models. I talked a little bit about, or maybe a decent amount about, on-wafer multi-line TRL calibration and the effect on W-band load pull, and showed a few examples of how you could use models which were kind of accurate, and finally showed a recent example of on-wafer W-band noise parameter characterization. Okay, so the obligatory question slide here. So I think that's it.
Thank you, Nick, for the very nice presentation. And yeah, the talk is open for questions. And by the way, there is going to be now in this very same room a full 2-hour session on load pool. So for those interested to this topic that you just introduced. But yeah, very quick Q&A. I see there is already one question in the chat, in the Q&A tab, please.
Yeah, so I see the question is, how about open short